Is the presentation visible?
Yes, madam.
Okay.
Madam, will there be any negative marking in the final exam? I think it will. There will not be any negative exam, right? So negative marking, right?
Yeah, I think there will not be any negative marking, but actually last day also somebody asked the same question. So I asked somebody from the NPTEL support team. They told me to post your queries. There is some discussion forum or some common group, WhatsApp group or something. I don't know. So they told to post that in the discussion forum.
Okay, madam. Okay.
Mm. Okay, I will start then. So good evening. Welcome to the second tutorial session of EMI, EMC and signal integrity, E42. And the course instructor is Professor Amitava Bhattacharya from IIT Kharagpur. Yeah, so uh, yeah, so this week's topic was the response of linear systems to periodic input signals and techniques to compute one-sided spectrum coefficient in a more convenient way. So last day also we solved some problems where we computed the Fourier coefficients and also one-sided Fourier coefficients, all these things, but the process was quite tedious. Now, if we want to do all these computations in in a more convenient way, there is a way we can do that. So that method and based on that method, some numericals we will discuss today. Okay. So just look at this problem. This is the first problem. A periodic waveform is defined by that the equation is given xt. This is a function of time. So this is a pulse waveform. So from 0 to tau, the value is a, and rest of the time period it is 0. This is a very common waveform. Last day also we saw that. This is a pulse waveform like this. In the x-axis, suppose we have t. So this is the waveform. Here we have tau, and if this is the time period, then from tau to t, the value is 0. This is xt. This is xt here. Okay. Okay. Now, what are the data given? The data are a equal to 1, tau equal to 1 second, and capital T equal to 2 second. Time period is 2 second. Tau is 1 second. Tau is till this point the pulse waveform there is it is high. So the pulse duration is basically 1 second, and A is the amplitude. Amplitude is 1. Then determine the value of C1n, and in subscript there is another one. So what does it mean? C1n, and in the subscript we have 1. Okay. So that, so if you, so in the lecture if you will see, what we can do is when we need to find out the Fourier coefficients. If you take any waveforms, this kind of pulse waveform or trapezoidal waveform, clock waveform, what we will do is we will keep on differentiating these waveforms until we get a an impulse function. Okay, so we will keep on differentiating this function unless we obtain an impulse function. And the impulse, we you know that the impulse response of a system, so you you must be familiar with this function. So this is also called Dirac delta function, delta t. Okay, and this is 0. This represents an ideal impulse function. At t equal to 0, it has infinite amplitude, but other than that, everywhere it is 0. Okay, here also and here also. Only at t equal to 0, it has infinite value, and if we integrate it, delta t, from minus infinity to plus infinity, only at t equal to 0 we will get some value, and the integral will give us 1. Okay, so this is the Dirac delta function or unit impulse function. So we will keep on differentiating this waveform until we get an impulse function of some strength. So this is an unit impulse, but for this waveform, if this amplitude is A, then your strength may be capital A or something else. Okay. And what advantage do we get? Once we get this impulse function, then we can compute the Fourier coefficients very easily. Okay. So have you seen the lecture how Professor Amitava Bhattacharya has computed, like what are the steps? Have you seen that lecture? Week 2 lecture
Yes,
I
madam.
am talking about. Okay. Yeah. So you must have seen that uh, basically if you just compute the Fourier coefficient Cn of this delta t, then you get like for unit impulse function you get something like 1 by capital T, right? 1 by capital T. So it will be the function is something like delta t, then multiplied by e to the power minus j n omega naught t dt. A second. Okay. And outside there will be 1 by t, of course. So this will give us 1 by t. Okay. So at t equal to 0, this value becomes 1, and delta t has only some amplitude at t equal to 0. Okay. So this, if this is unit impulse, then this gives you 1 by t. If if this gives you a, then it will become a by t. If this sorry. So if suppose if you just differentiate it, then the strength will be a, because here the amplitude is a, then you will get something like this here, and when it is falling down, this is a very sharp change, so here it will be minus a. Okay, so as simple as that. If we know this, then we can compute the Fourier coefficient of any function, linear, obviously any linear waveform. Okay, so let's come back to this problem. Now we will have to find out what is C1n and subscript 1. That means, because this is a pulse type of function, to get an impulse function, we will have to only differentiate once, right? If we differentiate this waveform once, then we will get this kind of waveform. So this is a here, and at t equal to tau, here we will get minus a, then again here we will get like this. So that's why this subscript 1. Okay, that means the differentiation has been done only once. Okay, and then C1n means, so if you differentiate it, you are seeing that we are getting two sets of impulse functions. One is positive, like arrow is towards positive here, then at t equal to capital T with a time period of t. If this is 0, then after this time period, we will get another one in the positive direction. Okay, like this is set 1. And then there is another set which is in the negative direction. That is at a delay of tau, at t equal to tau. Then again at t equal to t, capital T plus tau. Okay, capital T plus tau, like this. So the interval is always capital T, because here this is the time period. Okay. So this is the first set, set 1. This is the second set after differentiation. This C1n means that we are referring to the first set. Okay, referring to the first set of waveforms, impulse functions. In that case, I told you that as the strength is A here, then we can say straight away that C1n and then subscript 1, that will be what? Capital A by T, right? Capital A by T.
1.
Yeah, right. So capital A is 1 and T is 2 second. No, so the answer will be 0.5, right? What were you telling? You said something. You said 1. Okay, so the problem is understood, right? How will you solve it? So I described it a bit so that you will understand. But in the exam or in the assignment, if you want to do it, like it, you can do it very quickly. So Just think about how you can how you can differentiate it and get to this point where you can represent it as impulse functions after differentiation. Okay, then what you will have to do is you will have to find all these things. So here we require to differentiate only once. That's why this subscript one. If there are some more complex functions, you have seen the trapezoidal waveforms, all these things. In those cases, it may require that you will have to differentiate more than once, twice or thrice. In those cases, the subscript will keep on increasing. It may be two, it may be three, based on like uh, it will. So how many times you need to differentiate, based on that, this number will change. Okay, and this number means that uh, how many sets of waveforms are there. Here are two. So for some cases there may be three parts of a function. Okay, we may like divide it into three parts. So in that case it will be C1 and C2 and C3 and like that. Okay, so this is a very simple function. Okay, fine. So if you don't have any doubt, then I will go to the next problem. Consider a periodic waveform, the same waveform that we saw previously. A is given, tau is given, capital T is 3 second, calculate Cn for sixth harmonic. Okay. Now I will tell you a trick. So here obviously if you see that tau and T, but suppose you get some pulse waveform whose duration is 50%. What I mean to say is, if this is tau and this is capital T, so tau by T is 50%. That is 50% time the pulse is there, and the rest of the 50% it is zero. In those cases, if you see any even harmonic, if they ask you the value, the magnitude of any even harmonic like fourth, sixth, or eighth, like that, you can straight away answer this to zero. Okay, no need to calculate anything. Why? Because you can understand that this kind of waveform, they have some DC value, right? They have some DC value which we usually represent as C0, right? That is the DC value, average value. And then if we subtract this average value from the actual waveform, we will get something like this. Okay, we will get something like this, right? If you get something like this, then you can understand that this has half wave symmetry, right? Are you familiar with this term, half wave symmetry?
Yes.
So where xt is equal to, xt can be any linear waveform, linear. So this is minus x t plus capital T by 2. Okay. So if you see half wave symmetry, in that case, the even harmonics are always zero. Only odd harmonics will be there. Okay. But here tau by T is 1 by 3, 1/3. So we will have to calculate, right? So how will we calculate? We can calculate by applying this new method that in this week we have learned, by differentiating it. So as I already told that we will get two sets of impulse trains. First is in the positive direction, another is in the negative direction, like this, like this. Okay. So Suppose C1n we have already found out in the last question. This was A by capital A by T. Capital A by T, and C2n. C2n means the impulse in the negative direction. Okay. That will be A by T e to the power minus J in omega naught tau. Okay. So why this extra term? Because this this negative impulses are, this is time shifted by tau. This negative one starts at t equal to tau, and then at capital T interval it goes on. Okay. So there is this delay of tau. That's why this extra e to the power minus j n omega naught tau comes. Okay. So if there is any impulse function which is shifted by any amount tau, the expression will be this. Okay. Expression will be this. And then what will be Cn? Cn will be 1 by. So this, all these things have been derived in the class, okay, in the lecture. You can go through it, you can study it. If at any point you have any doubt, you can ask it in the theoretical portions. J, J omega naught, there will be n. Okay. J n omega naught, and here A by T, and another thing, this there will be a minus sign because its strength is negative. It is in the negative direction, that's why. So A by T, okay, and minus this one, minus this portion. Basically C1n plus C2n. Okay. To the power. You can also solve it simultaneously. And if you can, if you already have got the answer, you tell me. Okay. So this we will get. Okay. We know all the values, A, tau, capital T. Okay. And omega naught is what? Omega naught you can write it as 2 pi by T. So in the, usually you will see in the expressions, we manipulate it like we manipulate it and we simplify it to uh, to make it as sinc functions. Okay. If you can't remember all those expressions, just remember the basic till this point. You don't have to always convert it to a sinc function. Just compute till this point, and this way also you can find out the values. Okay. So can you tell what will be the sixth harmonic value? Put n equal to 6 and omega naught you replace by 2 pi by T, and then you can find out what is the magnitude for sixth harmonic. Can you compute and tell? A by T you can take common. A by T will go outside, and here within the bracket 1 minus e to the power minus j in omega naught tau. So in omega naught tau, this is 6, then 2 pi by t. So tau by t is 1 by 3, 12 pi by 3. That means it becomes, I think, 4 pi, right? So this is 6, this is 2 pi, so 12 pi and by 3, that is 4 pi. So e to the power minus j 4 pi. That means cos 4 pi minus j sin 4 pi. Cos 4 pi is what? Cos 4 pi is 1 and sin 4 pi is 0. Within the bracket, this is 1 minus 1. So the whole thing becomes 0. Okay. Is it clear? Is the
Yes,
solution
ma'am.
clear to everybody?
Yes, ma'am.
Okay.
Yes.
Okay. Okay. We will proceed to the third question then. Consider the pulse waveform with zero rise time and this is fall time, not false time. This is fall time. Okay. Just a second. Hmm. Yeah. Yeah. So determine the value of magnitude and phase of the fifth harmonic if the duty cycle is 50%, given amplitude of the pulse is 1 volt. So they have mentioned that the duty cycle is 50%. Rise time and fall time 0 means its slope is 90 degree. Okay. So there is no rise time, there is no fall time. If it would have been sixth harmonic, we don't need to compute anything. It would be 0. Okay. So magnitude. But we need to find out what is fifth harmonic. We can use this expression because the function is same. This is the same function, right? The only thing is that they have given the amplitude as 1 volt. So the amplitude is known, but the waveform, this shape is same. We can use this expression to compute the magnitude and phase of fifth harmonic, right? So J in omega naught uh, T. This comes outside 1 minus e to the power minus j in omega naught tau. Okay, this is the expression. So you can see the phase we can readily say. Okay, so phase there is plus 90 degree and minus 90 degree. So we have j over here. Okay, so most probably it will be minus 90 degree, but okay, let's just see. A is 1, n is 5, and omega naught t will be 2 pi, right? So 5, so this is 10 pi over here, and 1 minus, so here omega naught tau by t, and we can do so 2 pi into so 10 pi and So e to the power minus j, this becomes 5 pi, right? I think. So n is equal to 5, then 2 pi omega naught t, then tau by t is half. So this is 5 pi, right? This is 5 pi. Now cos 5 pi will be minus 1 and sin 5 pi is 0. That gives us 2 by j 10 pi. Finally, we get 1 by 5 pi, and what is the angle? Minus 90 degree, because j is in the denominator, that is minus 90-degree phase. Okay. So you can generalize this. I think in the lecture slides also you will get that for this kind of waveform, the odd harmonics are like this: 1 by 5 pi for fifth harmonic, then for seventh harmonic 1 by 7 pi, like this. Okay. And the phase is always minus 90 degree. Just check the slides once. I think it is already given. Okay, is it clear?
Yes, madam.
Okay.
Yes.
Okay. So let's try this problem. Consider a pulse waveform having 25% duty cycle. Amplitude of the pulse is 1 volt. Determine the magnitude of the fourth harmonic. Consider rise time and fall time of the pulse to be 0. Okay. So slightly different. How? Because here the duty ratio is not 50%, it is 25%. For 50% duty ratio, things are simpler. But when the duty ratio is not 50%, then we can't get a, a symmetric waveform. Okay, this is not a symmetric waveform. So suppose this is tau, that is 0.25, and then here we have suppose t, right? So this is the duty is 25%. Duty means the pulse duration with respect to the total time waveform, total time period. Okay, that is 25%. This duration starting from here to here, this duration is 25% of this total time period, right? That is called the duty ratio of a signal. And we need to find out what is the magnitude of the fourth harmonic. Okay. Hmm. Okay, so now just apply that same approach, differentiate it. We will get the positive pulses and the negative pulses, right? So the same way we can get A by, you remember that if it would have been a 50% duty ratio waveform, then readily we will go with this answer, option B. Okay. But this is not an symmetric waveform because the duty ratio is 25%. So we will compute it. J n omega naught t 1 minus e to the power minus j n omega naught tau. Okay. A is 1. So 1 by j n equal to 4, because we need to find out the magnitude of the fourth harmonic. j 8 pi. 1 minus e to the power. Here we have 4, then 2 pi, that is 8 pi. And tau by t is 1 by 4. So e to the power minus j, so 4. Then we have 2 pi. Then again 1 by 4. Because tau by t is equal to 1 by 4. We have 2 pi. So this is e to the power minus j 2 pi. Now you can understand cos 2 pi is 1. Okay, so this 1 and 1 gets cancelled. We get 0. So the answer is 0. Okay, here. This is a connected question. So you consider all this data and then determine the magnitude and phase of the second harmonic considering tau r equal to tau f equal to 0. That means the same pulse waveform because rise time and fall time both are 0. So this time we will have to find out what is the magnitude and phase of the second harmonic. Okay. Remember, this is also an even harmonic, right? Second harmonic. Earlier, we got the magnitude of fourth harmonic was 0. Let's see whether what we get for the second harmonic. Okay. J n omega naught t 1 minus to the power minus j n omega naught tau. Here also tau by t equal to 1 by 4 and a is equal to 1. 1 by n equals to 2 because it is second harmonic. So j 4 pi, within the bracket we have 1 minus e to the power. So 2, then 2 pi, 4 pi and 1 by 4. 2, then 2 pi, then 1 by 4. So j pi we have. Cos pi is what? Minus 1. Okay. So 1 by j 4 pi. Over here we have 2. That gives us 1 by j 2 pi. Okay. J 2 pi. Magnitude will be then 1 by 2 pi and the phase is minus 90 degree. Right. Phase is minus 90 degree. So you understood, right? How we are getting?
Yes, madam.
Okay. So here, if you see fourth harmonic magnitude was 0, but second harmonic is not 0. It is 1 by 2 pi. Okay. Because here the duty ratio is 0.25. But for 0.5, it would be 0. Okay. Now let's see this question. Consider a train of trapezoidal clock with unit amplitude and equal rise time and fall time. Time period of the pulse is 2 seconds. If C naught is 0.5, then calculate the pulse width. Okay, so here a different waveform is considered. This is a trapezoidal waveform. Okay, a trapezoidal waveform. This is time period T. This is the rise time. This is the fall time. Okay. This is the rise time. Tau var. And this duration is the fall time. Tau f. So rise time and fall time, they are equal, and time period is 2 seconds. Then what is the pulse width? Now pulse width, by the definition in the course lecture, it has been considered from uh, this point, suppose this point to this point. What are these points? They are
Tau.
tau by 2 and this is tau f by 2, right? So they are half 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 power max, like half of the maximum position, right? This is the maximum position, suppose A. So these positions are A by 2 and here also this is A by 2. So from this point to this point, the duration is tau. This is the pulse duration. Okay. So for okay, so I will just refer to the lecture slides once so that we can, so this calculating these values, they are not very difficult to calculate if you are already familiar with the process, how they are done. So yeah, so I think you also have this slides with you. You have access to these slides. So that's what I was telling you in the beginning of the session, that you will have to repeatedly differentiate the waveform until you get the impulse train. Okay. So for this trapezoidal waveform also it has been done. So yeah. So suppose this is the kind of trapezoidal waveform. From this point to this point you have tau. This is the pulse duration. Okay, this is the rise time. That means when the waveform rises from 0 to 100%, and this is the fall time when the waveform falls from 100% to 0% again. And this part is, there is nothing, it is 0. So if you differentiate it, obviously you will get first, you will not get any impulse, you will get pulse waveform. Okay, because this is the ramp. So if you just write it like this, I will go to the slide. Hmm. Let's take a new slide. Suppose we'll delete it. Okay. Okay. So this is the this is one cycle of this waveform. Okay. This is tower and tau wave. I already showed. If you differentiate it, you can understand from this point up to this point, this is a ramp, right? So the equation will be A by tau r t. That will be the equation. And if you differentiate it, then obviously you will get this kind of a waveform, right? Whose amplitude is A by tau r. A by tau r. From this point to this point, this is constant, so the differentiation is 0. The differentiation is 0. Then we have a negative ramp. So it is falling down from A to 0 again. Okay. So what is the waveform? The waveform is A minus A by tau f t, right? So if you differentiate it, you will get minus A by tau f. Because the slope is negative, that's why you will get a pulse in the negative direction. Okay. And what is the amplitude? Amplitude is minus A by tau f. Okay. If tau r is equal to tau f, then there is a symmetry and further simplifications are done. Okay. Now again, if you see, you are getting this and this at each cycle, right? And this one is familiar because we know what is these are the pulse functions. So if you differentiate it again the second time, then we will get the impulse functions here, then over here. So here you will get, then again here you will get in the negative direction, and here you will get in the positive direction, right? Like this. And this is still T, and then this pattern gets repeated, right? So now this is the step. We will have to get to the impulse functions, and we know what are the Fourier coefficient of an impulse function, right? And as we have we had to differentiate it twice. That's why outside this term will come twice. This j n omega naught, this term will come twice because the differentiation was done twice. Okay. So those things are already given in the lecture slides. Okay, so they have given the value of C0. They have given the value of C0, what is the pulse width. Okay. Now you can also for because C0 is the average value, you can also take a shortcut. The function is a trapezoidal one. You can break it into three different parts. Okay. Three different parts. This is tower, this is tau f, and this is a rectangle. What is the area of the first part? The area of the first part is half a tower, right? Because this is a triangle. Then the second part, this is part 1. Then part 2 is a rectangle. So a, suppose tau dash, this duration is tau dash. So a tau dash, okay? This is part 2. So this duration is I am referring as tau dash, okay? Tau dash. And then another triangle. So again half a tau f, right? This is part 3. Then what is the average? So summation of 1, 2, 3, 2 and 3, okay, by the total time period t. What do we get? So if tau, they have already given rise time and fall time, they are equal. Tau r is equal to tau f, right? So we get a tau dash plus tau r by T. Okay. Just okay. So T, I can't. I am not able to write here. Yeah. So A tau dash plus tau r by capital T. That is our average value. That is equal to 0.5. Okay. C naught. So time period is given 2 seconds and uh, okay, equal rise time and fall time. Calculate the pulse width. Okay. Unit amplitude. So capital A is 1 and this is 2. So tau dash plus tau r is what? That is equal to 1. Right? That is equal to 1. And what is the pulse width as per our definition? The pulse width is tau dash plus tau r by 2 plus tau f by 2. Right? That's what we discussed. Here tau r is equal to tau f. So the pulse duration is equal to tau dash plus tau r. Okay. This is equal to tau. And we have already found out this value is equal to 1. That is why the pulse width will be equal to 1. You can also refer to the formula. In the formula it is given that a tau by t is equal to c0. If you refer to the lecture slide, so c0 value you will get this. But suppose you don't remember this expression. In those cases, if the waveform is breakable, then you can break it into parts and find out the individual areas and what is the average, and from there you can get these values. Okay, this is just an alternative. If you remember this, then well and good, you can readily get the value from this formula. A is given, capital T is given, C naught is given, only tau value is required, so that you can get from here. Okay. Okay. So I will take a 10-minute break, then I will get back to the next problems. Okay.
Okay, madam.
Okay.
Hello.
Yeah, hi.
Hi guys, can you hear me?
Yes, I can hear you.
Yeah. So just I wanted to interact with you. I am also one of the enrolled student in this course. So are you from academia or you are from industry?
No, actually, I am doing my PhD in NIT Goa.
Okay.
For coursework, I have taken this subject in NPTL.
Okay. You don't have any industry experience.
No, previously I was working in industry for 8 years.
Okay. Which industry?
Tata.
Tata Motors or
No,
what?
no, Tata Advanced Systems Limited.
Tata Advanced System Limited, defense applications.
Yes, yes.
Okay, so you worked on system level or you actually developed any hardware in-house, uh, building circuits,
Yeah,
PCBs?
we were designing wiring harness for
Okay,
aircraft.
okay, okay. Okay, so basically I enrolled this course seeing a post on LinkedIn where the person who have posted said that it is a very good course for power electronics engineers who are into design domain, who are developing converters and inverter applications in from scratch in the working industry. So that's why I enrolled in this course. So I wanted to know whether in this one in first and second week I can see only numericals, okay, which is a purely a theoretical based approach. Will it help design engineers to actually develop good hardwares which will not have any issues like operating in environment like electrical fast transients, surge, electrostatic discharge, EMI, EMC compliance, all those things. Because I am working in industry from last 4 years, and my intent of taking up this course is not to do any math in the book. My intent is to develop hardware, power electronics hardware, and whether this course will help me design good hardware where all the, let's say if I am doing some doing these problems, and will it help me to, conclude on some things, like if I if I'm doing some calculations for component selection and topology selection, and if I'm going through this course, and will it help me to design a component converter which will not have EMIMC issues? That's what my question is, because uh, investing time is good thing, but it should directly or indirectly help me in the uh, actual hardware that I'm designing. So what do you think about this?
Yeah, actually, that's a good question. Even I too don't know. Maybe at the end of the course, we might be knowing the answer. Or you can ask madam
Yeah, yeah. Actually, I
once
just
she
I
comes.
just joined and she took a break, so I thought in meantime I can interact with you guys who all are
Okay.
there. Yeah,
I think madam can answer that.
yeah,
So you're writing the exam, right? At the end.
yeah. I am writing the exam. That's okay, but
Do you
see,
know that?
even if I score good marks in this exam, I will get a certificate. But at the end, in my company, they will not appreciate me only by the certificate. If that converts into something fruitful, and whatever projects I'm doing, there will be not any problems with respect to MIMC, then they will appreciate, right?
Yeah. Actually, my doubt is, do we have any negative marking in the exam?
No, 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 I don't know. See, I have not seen about that. I have just enrolled, and I will write the exam, that is for sure. But for me, marks doesn't matter. Even if I score 50%, it's okay for me. For me, marks doesn't count.
Okay, okay.
Mm. Other two guys are also from academia only, or anyone is from industry? Sarvesh and Gagan Rao.
I'm in industry or industry.
Okay. So which company are working?
Endurance technology.
Sorry,
Endurance technology.
endurance technology. So basically, what you do?
We design the ABS, two-wheeler ABS.
ABS.
Yeah.
Okay,
Anti-locking.
braking system,
Yes, that's correct.
anti-lock braking system.
Yes,
So
correct.
is there any electronics involved in that?
Yeah, when right now I'm my designation is testing engineer, system level.
Okay, okay.
Yeah, that's
So
why
system level, you are testing the system, the ABS system,
yeah,
whatever is
yes, that's correct.
designed.
Yes,
Okay. So
correct.
but you must be knowing, right, what goes inside. Is it a electronic solution or it is purely a mechanical solution? Because
Electronics
I
only.
don't know. I
They
don't
have
know.
two parts are there. First one is the ECU and HCU, two two there. EC is
Correct, correct.
completely electrical
Okay,
and
okay,
HC is completely mechanical.
okay. So if ESU is there, then it is a electronics thing, right?
Yes, yes,
So,
correct.
so while testing, you what all test you do, and what feedback do you give to design team? Like this is the issue, so you have
Yeah,
to
yeah, yeah.
do so and
First,
so
what
things.
we will, once they are designed everything done, we will check the basic of standards ISO 16750. Some
Mm-hmm.
basic standards are there. EMC testing, some standards are there, and
Mm-hmm.
mechanical related ISO standards and ISO 2626 and functional testing standard they follow. But
Mm-hmm.
in that one, we already conducted the EMMC testing at ARI Pune.
Mm-hmm.
You know the ARI Pune,
Yeah, yeah, I
that
know.
in that one they tested with they take the part as per our requirement. What is the input power supply? What is the output? What is the current? Everyone they will take it and they
Mm-hmm.
will follow the some standards. Then they will test
Okay,
it.
okay,
And that's why
okay,
in ARI they don't say the complete information.
okay, okay, okay. So, what is your intent to take up this course?
And this course means I have already last 2 years I have tested completely, but they not given fully knowledge. That's why
Mm-hmm.
they have some knowledge in ARI. After
Okay,
that, beyond the any knowledge, that's why I'm joined this.
okay, okay, okay,
Just know I also just know 1 minute before I joined when we
okay,
started
okay,
at the time. Yeah.
okay, okay, okay. So the first 2 weeks, I can see it is purely theory. So I am not able to relate where I can use this actually in the system hardware level. So if
Okay.
I'm designing a converter,
Yeah.
it
Okay.
may be any converter. So it may be for a motor driver, or it may be for a power
Yeah.
supply, DC to DC or
Yeah.
AC to DC, anything it may be.
Yeah.
But to have the comply to pass the compliance to sell in
Okay.
the market. Maybe we will have to pass CISPR 22, we will have to pass surge, EFT, electrostatic discharge, all those things we have to clear. Okay.
Yes. Yes.
So to at the initially when I start to design the converter, I will have to plan my activities in such a way that I will eventually pass these tests. So will this course mathematics will help me to uh, to to fulfill that outcome? That is what my question is.
Yeah. Oh, wait 1 minute. I will tell that. In normally what happened in generally you have develop any product.
Mm,
Basically, what they do in the
mm,
product you have connected the electrical cables.
mm.
In the cables, I have BCI testing, ALE, superimposed, and short circuit. They everything will come in the EMI, EMMC. Hello.
Yeah, yeah, right.
In that one, they check the what is the taken that wire cable, how much current they will take, how much magnet will generate. At that time, some other cables also. They in vehicle you have attached any equipment that means your product. There are some other products also that now right now observe that I am using ABS. ABS I will put in the vehicle, but at the
Mm-hmm,
same time display cables everything is there in that same bike.
mm-hmm,
They do not interact with the other one. If you connect that one
mm-hmm,
ABS, you have whatever working that ABS brake apply at that time you have generate any cable magnetic field, any surge current that will be
mm-hmm,
not affected the other one. They will give
mm-hmm,
that they means now how much level is there, any
mm-hmm,
affected in other one, what is the range. They will in
mm-hmm,
general EMS test mean they will give that only. But here
mm-hmm.
just now I'm seeing she explained only problems. I
Okay.
don't know. So
Okay,
once
okay.
the session will done, they will once we are asking
Mm.
what is that
Even
one.
even I go to external labs to test my hardware. So so it is a system level test basically.
Yeah,
Whatever
sure.
test we do in the labs. But when we are designing the any converter or any application, at the
Okay.
design stage we have to do some tests, right? Like for example, for radiated emission, we have to see while design stage only we have to do some radiated test. We have to do some conducted emission test while design only. So In that design loop, we will have to take some decisions like PCB layouting should be so and so. It should not be something that we have already done. So all those things, decision making can be done through the. Is there any outcome of this code in which I can do that decision while design phase, not after I had developed the complete product? So that's not that obviously that I have to do at the end, but while designing only I have to ensure that my product should pass so and so test. So what how should be my PCB layout, how should be my component selection, how should be it placed in the system. So all those things I should be able to make decisions in the design phase.
But in the design
For
phase, you
that.
take a decision. After that, if you have, as per your as per your guided, this is the input voltage. For example, you have taken the 10 volt 10 volt input and some 10 amperes current. That is your input entire board, correct?
Mm-hmm.
After that,
Hello. Sorry to interrupt your discussion. Actually, yeah. So actually, what I wanted to say is that yeah. So actually, I understand your concern because I myself is doing PhD and I am also actually I my application is in EV charger domain only. So I am working on designing EV onboard chargers, AC to
Mm-hmm.
DC converters basically.
okay.
Mm-hmm.
So yeah, so if you like in academia, I'm not sure like this is not a very I don't know very mm, immediate issue. So even if you are designing one converter in lab, you are able to test it at a certain power level. You are able to show the results. Then it is okay. But obviously in commercial space where you are actually designing a product. So I think EMI EMC is very important. So you will have to
Yes.
pass those.
Correct, correct. If
Yes.
any product we
Yeah,
So.
develop, they ask the
yeah,
main testing. If you input power supply at the time also, they will check. If sometime you normally you have connected
right.
battery, the battery not properly give the as per what's your requirement power. Sometimes it will
Mm-hmm.
fluctuated.
Yeah, yeah.
Correct. That will
Actually,
be
yeah,
taken.
some of my friends are also in industry, so they are in some of the like companies where like they make those products like micro inverters or EV
Mm-hmm.
chargers also. So
Mm-hmm.
they are like very involved in those EMI EMC based tests. I sometimes talk to them.
We
But yeah,
also involved right
actually,
now. Our product
yeah,
also we recently last 1.5 year back we tested the ABS.
yeah.
Completely now in product we launched in all the customers in Bajaj our customer. Also our
Mm-hmm.
product will right now working. But generally, continue. I will tell first. Continue.
Yeah, yeah. Actually, yeah, I understand. Actually, I think like the till this point, what have been covered in this course, mostly they are like very theoretical. So all these computations and all, and I think in industry, like process, the things are not done in this way. Like first, like, but I feel like, see, the point is, so whatever practical approaches we have developed, so all these things come from some theoretical foundation, right?
Yes.
Because
Yes.
unless,
That's true.
so unless like whatever tests you do, whatever calculations are done in computer or some software, so
Mm-hmm.
behind those things, or there are some theoretical foundation.
Mm-hmm.
So now if any student or somebody like you guys are very experienced, but if any student is suppose trying to understand this,
Mm-hmm.
so what will like if they don't have any theoretical foundation, they will not understand anything like why we are doing all these things.
Mm-hmm.
Like so I think suppose for example for when you are doing EMI EMC testing for, so there is a spectral analyzer where you see some quasi peaks or something of some of the harmonics, right? It shows like which harmonic is what is the peak of these harmonics, and there are various standards, international standards, so they impose some limits, so this harmonic should be limited within this value, right?
Mm-hmm. Correct.
If I am correct, like you will know better than me because you are like you are doing in industries, but Like I have only seen it once in spectral analyzer, so they show some peaky like this kind of things,
Mhm.
and the
Mhm.
bandwidth is I think 150 kilohertz to 30 megahertz. Like
Mhm.
usually they specify
Difference
in
are
this
there based
limit.
upon our requirement. It will be difference also there
Okay,
based upon
okay,
our requirement as per our product requirement.
okay,
We
okay.
have
I think
some
for
maintain
like
some stand. Yeah.
for I think for these converters, specifically for EVs, I think like I read some documents where they were specifying that 150 kilohertz to 30 megahertz, but yeah, it may be different. I am not very sure about those things.
Yeah, ma'am,
So,
but I understand.
uh-huh,
Sorry for interruption.
uh-huh.
I don't know whether you were listening to our discussion while you were on break or not. So I just wanted to ask, uh, uh, state my concern in one sentence once again. See, I'm designing a power electronics application in various applications.
Okay.
Maybe it varies from AC to DC, DC to DC, or DC to AC inverter application. Okay, so even
Hmm.
if we talk about motor application,
Mm-hmm.
there is also a AC to DC stage, DC to DC stage, and AC to DC, DC to AC stage, because there is an auxiliary supply required to
Right,
power on your inverters. Okay,
right,
so
right.
on a single board, I have I have inverter module. Also,
Mm-hmm.
I have one auxiliary supply that powers the
Okay.
auxiliary gate drivers and other things.
Mm-hmm.
Okay, so
Understood.
now
Uh,
both the things operate at different frequency, switching frequency and operating frequency level. Okay, so in this thing, we as a design engineer have to take a call. What will
mm-hmm.
be our switching frequency for the power topology? What will be the switching frequency for our auxiliary supply and other things, right?
Right,
Because
right.
those things
Mm.
will interact with each other because they are sitting on a single PCB. Okay,
Right, right.
and we know that we want to pass CISPR 22. We want to pass electrical fast transient, we want to pass electrostatic discharge, we want to pass surge immunity,
Right,
all those
right,
things we want
right.
to pass to commercialize the product. Okay, so
Right.
obviously we go to external labs, enable certified labs, to test our final product. Okay, but
Okay, okay.
that testing a final product is okay, anyway we have to do it. But if we fail the final product, then we have to redesign the entire topology, we have to redesign the entire circuit, we
Yeah,
have to
yeah, yeah.
redesign the entire
Yes, yes,
PCB.
yes.
All this task is not a 1 week's task. Okay, it takes 2 to 3 months. So
Mm-hmm.
to deliver the project in time, if
Hmm.
I am well aware of the things, like if I know that this layout will not work. Okay, or let's say this switching frequency of auxiliary supply will create EMIMC issues in future. Okay, so
Right, right.
if I can quantify the things
Mm-hmm.
well before the product is finalized, so
I understand. I'm
knowing,
understanding.
yeah,
Actually,
yeah, yeah.
so
Hmm.
in the initial phase of the design, you want to cut out all these things so that
Hmm.
like
Yeah, you
you
tested
can
it
pass this.
individually. Tested. We
Yeah.
have
Hmm.
the
Mm-hmm.
system level test
Because
before
I
we
am
have
not
tested them.
working
There will
only
be
on the system level testing or system level
correct, correct.
applications
But
like
Yeah.
before
EVs.
that,
I am
Mm-hmm.
working exactly on the PCB level. Okay, so all the MOSFETs or IGBTs that are going in the system, that I will have to select. What
Yeah,
should
yeah,
be the switching
understood.
frequency I have to select. What should be the
Mm-hmm.
gate driver topology that I have to select. Okay, so if all the things are in my control, then
Mm-hmm.
then this maths going behind this topic should help me in the design stage itself, so that final product which has been developed should
Hmm.
not have scope for redesign. Okay, I should be
Yeah,
sure
yeah.
that doing these things in the design procedure will
Mm-hmm.
definitely pass my product when it is finally ready. Okay, because
Yeah,
we
yeah.
don't have project timeline of 3 years, we have project timelines of, let's say, 6 months. Okay, in 6 months
months
we
of
have to
time, months
develop
of
a
time.
product, we have to test it, we have to
Mm-hmm.
clear all the compliances, and we have to launch it. Okay, so
Yeah, yeah.
so because of this, I wanted to know from you. See, it's only 2 weeks, and I am going to finish this course. I am going to write the exam also. That's a different thing. But
Mm-hmm.
after the course, I should be in position to have something on paper, so that I can take decisions while design. Like I cannot go with this component or I cannot go with this switching frequency because it will have some problems, EMI EMC related problems in future or at the end of the system level. And I will choose so and so component. I will choose so and so switching frequency of the auxiliary supply and topology, power topology, knowing that this will not create any EMI EMC issues. Okay, so
See, no, no.
uh,
First of all, let me just say this that whatever switching frequency, like if it is a high frequency PWM, you will obviously have to do pulse width modulation, right?
correct.
Whatever topology you are using. So
Mhm,
EMI EMC, like it will come. Whatever, like there is no any particular switching frequency you will have to choose for which like your product will go through at any
mhm,
stage. Okay. So switching
mhm,
frequency, if you are doing high frequency PWM, there will be some dB by dt for in the switches, right? So
mhm,
if you are not being able to do soft switching, you know, right? What is soft switching?
mhm.
So
Correct, correct, correct.
in those cases, if you are suppose using SIC or GAN or also simple SI also,
Mhm,
whatever like wide band gap you are using.
mhm.
So if there is high dV by dt or di by dt, there will be EMI EMC. All these things will impact your things. Okay.
Yes, yes.
So what I will, like honestly speaking, like I am also learning only, right? So I
Mhm,
don't know how much this course will help you because you guys are already like actually doing those tests. So and
mhm,
this course is what I think basically very theoretical oriented. So in
mhm,
terms of PCB design, how we will do the layout, how we will place the components, what should be the distance between the signal side and the power side, all these things, isolation. So I'm not
mhm.
sure whether those things will be covered here, okay, or there is any scope for covering here.
Thank you.
But yeah, so if you know, like I will just tell you, maybe you already know this. So
Mhm,
we were discussing this range of this frequency, right, where we considered the EMI where this EMI starts. So we
mhm,
consider starting from what I know is 150 kilohertz to 30 megahertz, right?
mhm,
This is kind of like there may be some other ranges also based on the application. But if we consider this one, so I have seen people making converters where they choose suppose they are switching frequency. So as we increase the switching frequency, our passive size decreases, right? That is one
mhm,
advantage of increasing our switching frequency. Our inductor size, capacitor size, all these things
mhm,
reduce.
mhm,
Now I have seen that they have people have chosen switching frequency. Suppose we could have chosen 100 kilohertz, right? Or suppose we could have chosen uh, 100 kilohertz. So in that case, it's second harmonic. Suppose 200 kilohertz. Okay.
mhm,
Or if you say like third harmonic, that comes directly in this range 150
mhm,
kilohertz to 30 megahertz. So we kind of there are many optimizations you can do in terms of your efficiency improvement. Also there is switching frequency plays a big role because your switching losses will be affected by your switching frequency.
mhm,
So you can do optimization, multi objective optimization, whatever, I don't know, like. So you will have to choose a switching frequency so that your and as your harmonics increase, their magnitude reduces. So fifth harmonic will be 1 by 5, like in this ratio they will reduce, right? So 1 by
mhm,
5, 1 by 7. So suppose you are seeing that if you choose 75 kilohertz, then in other aspects it is very advantageous in terms of your efficiency improvement and all those things. But if
mhm,
you slightly reduce it from 75 kilohertz to suppose 70 kilohertz,
mhm,
so you will get one advantage. What is the advantage? Because you see the second harmonic 140 kilohertz, it is outside of this range.
mhm,
140, it
mhm,
doesn't fall in this spectrum, right? 150 kilohertz to 30 megahertz. So
mhm,
but if you are choosing 75, then 150 kilohertz is just at the starting of the spectrum. So you will have to consider that harmonic also. And what is the advantage? Then directly the third harmonic comes at 210, right? And it
Hmm.
will decrease by a factor of one third. So your magnitude anyway reduces, right? So as the harmonic order increases, your magnitude will keep on reducing. So some this kind of like selections are done, like I have seen. But yeah, like I am also learning, so I am not very sure about the exact measures that which are taken, or like you
Okay.
understood, right?
Yeah.
What I
Yeah.
tried
Yeah.
to.
Understood. Yeah.
Yeah,
Understood.
yeah, yeah.
Understood. Yeah. I'm not doubting on the course outcome or a course content. That's not my question. I just wanted to have clarity on the things like whether this will
Hmm.
help me in the design stage itself. After it is passed or failed, so I'm not learning anything. But
Yeah,
if
yeah.
this whatever I'm learning in this course, whatever mathematics I'm doing, Fourier
Mm-hmm.
transform and all those things,
Mm-hmm.
it should convert into a product that has a minimal EMI MC issues because I know this course. I have done this course. So that's what my question was.
Yeah, I'm not sure actually. You can ask them, like if you have any discussion forum or some group, or somehow you can connect, because I told that I don't have any direct connection with the course coordinators or somewhat. So
Okay. So
you can
you
just
must be
ask
working. You must
them.
be working with Professor Amitabh Bhattacharya, right?
No, no, not really. Actually, I am in some other, I am in IIT Delhi, and he is the professor of IIT Kharagpur. So
Okay.
we are PMRF scholars. So we get one
Okay.
scholarship as part of
Okay.
our like this fellowship. So we
Okay.
are supposed to do like do this TS teaching. We are supposed to
Okay.
work
Okay.
as teaching
Correct.
assistants. Okay.
Okay. I
So
assume
I
that you work with
no,
him.
no, 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 no.
Okay.
No, it doesn't
Okay.
work this way. So, like we just have to select the courses, and they
Mhm.
intimate us, okay, now you will have to take this course. So that's how
Okay.
I got this course. Okay,
Okay.
I'm not working.
Is there any way by which I can directly ask questions to Professor Amitabh Bhattacharya so he can directly receive my queries?
I am not
Yeah,
sure
you can
whether
get
they.
his,
Yeah, yeah, yeah.
actually
If
his
you
mail
know,
ID is his mail ID is available in the website.
Okay. 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 Okay.
you
Okay.
can try to mail him, but I don't know whether he will like
You will check, you will see and
you
check. It
will
will
get
take
any
time.
reply or not.
Okay. No,
But
since it is his course, I thought maybe he should take one live session to interact with the students. He himself
I
should take
think
one live
in
session.
actually in some courses the course coordinator directly talks with the students, actually takes
Yeah,
sessions
that is a
in some courses.
that is I think so. That is a different
Yeah.
course series, not from Swayam.
Okay, okay. Acha, acha. Okay, then okay, you can try, actually. You can mail him or try through NPTEL, like if there is, I'm not sure actually what, if there is any common group where all the student members are there and also the faculty member is there. I'm
Mhm.
not sure. You can try to mail him actually. But yeah, like for you guys, like the people who are actually working in industry and they want to uh, gain some knowledge in terms of PCB design and all those EMI filter design, all those things. I am not sure actually, like at least in the initial phase of this course. So
Mhm.
I am not sure how much you will gain from this one. So yeah,
Okay.
because
Okay.
yeah, so
Okay.
I
Understood.
think,
Understood.
okay, okay.
Because I am not here for credits. I am here for only knowledge. Credits
Yeah,
are
yeah,
just a byproduct.
yeah, yeah, sure. Yeah, yeah.
Okay, we can
Okay,
continue
okay,
with the questions, whatever you're doing.
okay, okay. Yeah, I think till question 6 we covered. So, question number 7 we can discuss. Determine the phase of the fifth harmonic for the one-sided spectrum if rise time is 0.5 second. Okay. So these questions are basically like this only. Either you will have to find out the phase or the magnitude. Okay. Although magnitude spectrum is more important in case of EMI, but yeah. So this kind of questions you will get in your assignments. Yeah. So these equations, I think you already have these equations from the lecture. So as I was saying, this C0 value is already given in the last question we saw. And this is the magnitude, okay? This is the magnitude of the one-sided spectrum. So if you follow that differentiation process, so you will be able to get to the magnitude and the phase in a more like in an easier way than the last way we were doing all those integrations and all. Okay. And this is the phase. If you can remember, okay. If you can't remember, that is also fine. So just you will have to give a little more time to get to these equations. Okay. If you know the process, you can derive them. So fifth harmonic rise time is given, and what we need to find out the phase, right? So this is the phase. So just replace these values. So tau, I think what was the tau value? 1 second. So that we computed in the last question 1, and it is 0.5. The rise time is 0.5 and the time period is 2. Okay. Then what we have, this is 3/4. So 5 pi into 3/4. What does it give? 15 pi/4. In degree, you can convert it in degree. So pi, just replace it by 180 degree. And we just calculate 50. Yeah, so the answer is 675 degree. Okay, this is the answer.
Madam, can you show me that solution once again? I will take a screenshot. Yes. Okay, thank.
Okay, you will get this equation you will get in the lecture material also. Okay, so
Okay, thank you.
and the derivation of this, like how this expression is coming, this magnitude and this phase, how they are come, how we are getting to these expressions, they are also derived there. You just look at it once, okay? Just don't just memorize them. Just look at the derivation and see how it is done. Then I think you will remember better. Okay, so for a trapezoidal pulse width with time period of 4 seconds and rise time of 1 second, consider the following data. Phase of the second harmonic is 180 degree and magnitude of the fifth harmonic of for one-sided spectrum is this. Then calculate the pulse width if tau r is equal to tau f. Again a symmetric trapezoidal waveform where rise time is equal to fall time. Okay. So we will have to calculate the pulse width, right? Now if you see phase of the second harmonic is given. Okay. So you refer to this equation. What is the phase equation? N pi tau plus tau r by t. That is equal to 180 degree. So n pi to tau plus tau r by t. That is 180 degree for second harmonic. So pi you will have to, so this is in degree. So this side should also be in degree. So 2 into 180 tau is okay, rise time. So tau we will have to find out because that is the pulse duration, and tau r is given 1, capital T is 4, that is the time period, is equal to 180. From both sides this gets cancelled. So tau is what? 2. So tau is 1, right? Tau is 1 second. Okay, next problem. Calculate C naught and amplitude of the trapezoidal pulse. So C naught, we know what is C naught, that is the average of the waveform, A tau by T. Okay, this is the value of C naught. And we will also have to find out the amplitude A. Okay. You see another information is given. The magnitude of the fifth harmonic for one-sided spectrum is also given. Now we will have to utilize this data to find out the value of A and the value of C naught. So we will have to refer to this equation, which shows us the magnitude for a particular harmonic order. And here we have the value of fifth harmonic, right? We have the value of fifth harmonic, yes, for one-sided spectrum. So we will have two equation, okay? So the first one will be 2a, tau we got 1 second and t is 4. So 2a by 4, and then so n pi, so n is equal to 5. So 5 pi, and this is 1 by 4. So 5 pi by 4 sine 5 pi by 4, 5 pi by 4, and here also 5 pi by 4, and over here we have sine n pi tau r by t. So tau r was 0.5. So 5, this is 5 pi by 8 and 5 pi by 8. Okay, 5 pi by 8. That is equal to the value that was given in the question, some 0.0168 something. What was given? 0.01621. Okay, this is one equation. Another equation is, sorry, yeah, another equation is from the phase we can get, right? Hmm. Yeah, so from this equation you can calculate the value of A, right? You have all the values, you can calculate sine 5 pi by 4. So this you can calculate, this you can calculate, you will get the value of A. Okay, so let's calculate, let's see. We just mm, sin 125 divided by 4. This side we have a by 2. This is minus 1 by root 2. It is coming. Then below we have 5 pi divided by 4. Here we have 3.926. Okay. Then we have divided by 8. This is 0.923 and 5 pi by 8. Sorry, this is not equal to, this is multiplied by, sorry, 5 pi by 8. 5 pi by 8. This is 1.963 equal to 0.0168. Okay. So correct me if at any step I have done wrong. Okay. Just correct me. Okay. Okay. I think 6 to 1. I think I have done something wrong in the calculation. 1.963, 3.926. Okay. 2.74, 193. Okay. 2. Okay, so I think the correct answer is B. It is A is almost equal to 1 and C0 is 0.25. Okay, this is the answer.
Ma'am, in the exam, there will also be theoretical questions also, na? Along with problems.
Uh, Mostly like you have completed week 1 assignment and week 2 assignment. Have you completed?
Yes, ma'am. Yes.
So I think mostly there were numerical questions like this only, right?
Yes, ma'am. Only few theory questions.
So in the exam also it will be like this, mostly numerical questions and a few theoretical questions maybe.
Okay, madam. Okay.
Okay. So like so that's what I'm saying, like even if like see this way, these expressions are not very straightforward, right? So there are a lot of things going on, sine in pi by tau by t. So I think you just try deriving these things by yourselves once or twice. If you do it, then I think it will be better, because if you just straight away try to memorize them, it is difficult. And you shouldn't also do like this, these expressions I'm talking about. So just try to see like how these things are derived, right? So first, as I was saying at the beginning of the session, that you have like whatever be the shape, like if this is a linear waveform, then just differentiate them and try to see what you are getting, right? Then come to a point where you will get the impulse functions. And once you have got these impulse functions, you know what will be the Fourier coefficients, right? So a by t, and then e to the power j in omega naught, and by some alpha. So if alpha means what is the time delay to a impulse function, what is the time shift, and you will have to get this expression for each impulse in a time period. Okay, there may be three, like two or four, whatever is the number, and you will have to sum them. Okay, so all these things are given in the lecture material. Okay, so if you just see this process, see here there is this waveform, right? This is the trapezoidal waveform. What they are doing first, they are differentiating. If you differentiate this waveform, you will obviously get in this portion this pulse. Here also you will get one pulse, right? So the differentiation is done. And this times are specified here, at what time they are rising, they are falling. Then again they are differentiating. Now we have got these impulse functions, right? See, then you will have to just sum them. So the first one, its magnitude is a by tau r. So a by tau r 1 by t, right? And then here there is some exponential term. Why? Because it is shifted from the origin. It is shifted by this tau r time, right? At tau r, this impulse is coming. That's why this term is also coming, this exponential term. Okay, then like this for each impulse function, you will have to write like this, and you will have to sum it. If you sum it, you will get this Cn. Why this is 2? Because you have differentiated twice. You have differentiated the original waveform twice, that's why this 2. Then once you simplify this, simplify this, and finally you will get to these expressions. Okay, this is the way. And if the rise time and fall time are same, then you will get this kind of an expression, Cn plus, the one I wrote, right? So this is the final expression. This is only valid if your rise time is equal to fall time. So the rising slope should be equal to the falling slope. Then only you will get this expression, and this is the phase. This is the magnitude, this is the phase, and this is the average. This is the average of the signal. Okay. So like this is the process you will have to follow. Okay. Okay. So if you have any question, you can ask from today's content.
Actually, this semester, actually, I'm in NIT Goa doing my PhD first year.
Okay,
I have to take 4 subjects. I have to finish 12 credits. So
okay,
my professor suggested me to take NPTL. So only one course I'm taking from my college, and all the other 3 courses are from NPTL.
okay,
Uh,
okay.
so actually, I'm worried about my credit. I should have minimum 7 CGPA to get my to complete my coursework.
Okay, what are the other courses you are taking other than
Other
this?
courses are electric vehicle and motor drives.
Okay,
That is from IIT Delhi.
okay. Is
And
this by Amit Jain, sir?
yes, yes, correct.
Okay, okay, okay,
And another course is from Smart Grid IIT Roorkee.
okay,
Another one is Fundamentals of Power Electronics from IISc Bangalore.
okay. I think that is from Umanand, sir. Fundamentals of Power Electronics.
Yes, Umanand sir, yes.
Okay, okay. Ah, okay. I think Umanand sir's course is like, I think you will do good. Like if you just practice a bit, that is not very difficult or very
Y-
complicated.
yes, yes.
Uh, Actually, I once or did the TA for the fundamentals of power electronics that course. So I think that course
Okay.
is good enough. And this electric vehicle one, yeah, you just study a bit, and I think they are also you can expect mostly numerical questions. Okay.
Okay, okay. Actually,
So yeah.
previously I was working in Tata Advanced Systems Limited for 8 years.
Okay, okay,
So we recently we have I have communicated one paper in journal,
okay.
SCI
Oh,
journal.
okay,
In
nice.
So that is based on EMI EMC. Actually, I have developed at CPM for cross mitigation, chain
Okay,
parameter matrix.
okay.
So I was expecting that type of things in this course. So I took the course, but this is
Yeah.
actually different. Yeah.
Yeah, actually, that is the problem. Actually, actually, in the initial weeks, mostly the theoretical parts will be there, the Fourier transform. Then maybe towards the ending, you can get some practical aspect. Like I think sir told that he will discuss LISN, then maybe the EMI filter design,
Okay.
because yeah, I am not sure actually. I will have to see the course content, but yeah, mostly the first part will be theoretical mostly.
Okay.
Because I
Okay.
think
Thank
this
you.
is an introduction, like introduction to EMI and EMC now. So this is very textbook. Like how you will get in textbooks the theoretical foundations, the derivations, then the all these things.
Yes. Yeah. Thanks, madam.
Yeah, yeah. Okay, okay. Okay, like so if you guys need any help, like if I am able to give you like help you in any way, you just communicate, okay? But yeah, so honestly, like all the aspects of this subject is not even clear to me, because yeah, I am also here to learn. I am here to like take these sessions, but I am also here to learn. I need to learn the EMI EMC thoroughly. That's why. Yeah. But yeah,
Okay.
if I am
Okay,
able
madam.
to
Thank you.
help, I will definitely try to help. Okay. In any case, yeah. In this subject or any other, if you have any doubt.
Okay,
Okay,
madam.
then.
Thank you.
Okay, then. Let's conclude today's session. We will meet next week. Okay. Okay. Thank you for joining.
Thank you.
Yeah.
Thank you.
Yeah. Thank you.